Okay, hello everyone. I just emailed out the mini exam 6, which will be due a week from Wednesday. And I put on there, I'm really hoping we get through enough of the material to get you prepared for that. If for some reason I don't get through what I need to get through, I'll postpone the due date on that. But we have a lot to do, so I'm going to get right into it. If y'all are ready to go, let's get into 13.2. So at the end of class last time, I talked about parametric curves and how we can use parametric equations to draw curves using the parameter t. That's a little different than our standard functions like y equals f of x. We need that to be able to do line integrals. So I think if you're a little confused on it, let's just work through some problems and you'll hopefully start to pick up on how we implement the parametric equations into these line integrals. So geometrically, I already showed this to you. The idea here is that we have a surface, right? A surface is some function of two variables, f of x, y. So we're given some function. And what we do is we restrict the domain of that function to some curve in two-dimensional space, which would be some curve on the ground. We plug only those points into the surface and we get a curve up on the surface, that blue curve there. And then what we're doing for a line integral is we're dropping like a curtain that comes down from that curve up on the surface down onto the ground. And the line integral represents the numerical value of the area of that curtain. Okay, so that's the whole goal, is what's the area of that green curtain, so to speak. All right. So to do this, we go back to Cal 2, and this is where I started talking to you about this picture right here, which what we need to do is find the area of this little rectangle along this curve. And so to do that, let me get my marker here. We need to find the length of this piece right here. That'll give us the width of the rectangle. The height of the rectangle, well, that will just be the surface function evaluated at some point in that rectangle. So to figure out the length of this bottom piece, that's the hard part. That's really the most difficult part of the whole thing. The way we can do that is we can look at that curve on the ground, and that little piece of rectangle that we're talking about is like from here to here. So I'll put it in black. We're trying to figure out how long that piece is. And so if we draw a little right triangle here, it turns out that it's the hypotenuse of this triangle, where this is our change in x and this is our change in y. And so if you use the Pythagorean equation, we know that that will just become the square root of the dx squared plus the dy squared. Okay, the big thing is that because this curve is parametric, the x is some function of t, I'll call it x of t, and the y is some other function of t, y of t. And so when we talk about dx and dy, we're actually talking about the derivatives of these parametric curves, or each of the, not components, but each of the functions that represent the x and the y coordinate. So that's where we get that length on the bottom. It's just that square root there. And then of course we multiply that by the height, and that will give you the area of one little piece. And then we use the integral to add up all of the rectangles along the entire curtain. And of course, in the limit, we let the width of the rectangle go to 0, and that's what gives us the total area, right? So that's the basic idea. We're just now going to get to the actual formula. So here it is. Let me make this a little bit bigger. Okay, so let's start with this right here. I think it's easier if we start with that part first. So what this is saying is we are going to take the function and evaluate it at some point along that curve. So this, again, that little rectangle here, we're going to take some point in here, okay, and we're going to evaluate the function there. at some point, and that'll give us how tall this piece is, right? That's this piece. So this is the height of the rectangle. And then this whole thing is the width. And I told you a second ago that was going to be the square root of something, right? So there it is. It's the square root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared dt. So we add those all up. So we integrate those and we go from a to b. Now it's very important that you understand that the limits of integration here are not your limits of integration on x or y. It's actually your restrictions on t. So remember, t draws the curve on the ground. And so you want to start at a, that's the beginning of the drawing of the curve on the ground, then you end at b, and that'll finish off the whole. In this picture I showed you was that half circle, right? So all of this, okay, we have a new notation for this type of thing, and here's the notation for it. It's a single integral sign over c, where c is the curve on the ground, of the scalar function f of x, y, that's our surface, and this ds, it's d with a small s, really represents everything here. Now, I'm stressing that the ds means this because later on, we're going to have d capital S, and then even later after that, we're going to have d capital S vector. So we need to distinguish. We're not dealing with those yet. So when you start to look at like the big picture of things now, like all the integrals we've learned, like starting in Cal 2, we've had integral with like dx out here, or maybe dy. We've had double integrals where it was with respect to area. We've had triple integrals with respect to volume. And now we have this new integral that is with respect to little s, which we call the line integral with respect to arc length. And the arc length comes from the idea that that square root of that stuff really just represents the arc length of that curve. Okay, that all makes sense? Questions? All right. So here's our first example. And this is actually, this example is going to find the area of this green, where is it? This green curtain right here, we are going to find the area of this right now. Okay, so the problem that we're about to do represents this physical situation that we see in front of us here. All right, so we want to find the line integral. We know that because there's a single integral and it's over c. C represents some curve. Here's the function, the surface, and then here's with respect to arc length, ds. And then they tell us in here what c is. So c is the upper half of the unit circle. And I put this here, this is the formula that we're going to use just so we can have it as a reference. Okay, so first things first, we have to figure out how we can draw c using parametric equations. So let's take c and put it in its parametric form. In other words, we want to figure out x needs to be some function of t, and we need y to be some function of t. And we're trying to draw the top half. Oops, wrong. We're trying to draw the top half of the unit circle. So we're trying to draw that. Okay, so what do you think? We talked about this last time. How can you draw a circle using parametric equations?
I feel like I might be overcomplicating this, but would we first solve for y?
Okay, yeah, you mean take this and solve for y?
Yeah.
Well, then what you would be doing is you would be getting y as some function of x, and then it would be something, right?
Yeah, but then we would have, like the square root positive or negative, and then we only take the positive, and that would give us the upper half of our unit circle.
Correct, but it would be y as a function of x.
But then we can turn that into a parametric, which
Okay.
should be very
Just
easy.
turn the parametric we already have with cosine and sine.
Yeah, so hold on, Daniel is correct. We could take this, say y is equal to this, and then only take the positive part. I agree. And then the easy conversion to parametric from there is to just let x be t and let y be equal to the square root of 1 minus, in this case, t squared. Is that what you mean, Daniel?
Exactly.
Yeah, we could do that. That would draw it. And what would our restriction on t be?
It would be between -1 and 1.
Between -1 and 1, because that's t is really x. I agree. That would work. That would work. Now, is that the most efficient thing? Not really, because look at what we're going to need to do. Inside the integral here, we're going to need to take the derivative of x with respect to t. That should be easy, right? Derivative of x with respect to t should just be 1. Agreed? Here's x with respect to t, so take derivative on both sides, you get 1. But then we need the derivative of y with respect to t. That might be a little more complicated because we have square roots. It could probably be done. I think the more efficient way, though, is to use the power of the sine and cosine that we've seen before when we're trying to draw things that look like circles, like almost like in polar. And that is to make x be equal to cosine t and y be equal to sine t. And if you do this and let t go from 0 to pi, then you will in fact start out, you know, at 0. If you plug in 0, you get cosine of 0, sine of 0. That gives you this point. And as t starts to vary through pi, you start to draw the circle. Right? So Daniel, I'm not saying what you're doing is wrong. I'm saying that this choice, I think, will make our math easier. Okay? So I'm going to say up here on this one, I'm going to say question mark for this, because we could possibly work that out. Okay? And something tells me Daniel might actually be doing that right now. But I'm going to continue with this. Any questions on this, though, on why I've chosen this? All right, so now, where's my cursor? Okay, so now we continue here. Let's figure out these two pieces. I need the two derivatives. I'm going to need them, so I may as well take them now. The derivative of x with respect to t, that's just negative sine t. I'm going to need the derivative of y with respect to t, and that will just be cosine t, right? So I'm going to now take this integral and I'm going to start writing it down. The integral is going to be going from a to b, where a and b are the restrictions on t, which for us is 0 to pi. Now understand I only went to pi because we want half the circle, right? Not the whole thing. And then this right here, f of x of t, y of t. That means you're going to take the original function that we're integrating, which is this right here, and you're going to replace the x with what we are saying x is. So this becomes 2 plus, let's see, x is actually cosine t, but we have to square it because it's x squared, and then times y, and y here for us is sine of t. Okay, so that is the function converted over to the function evaluated along the parametric equations. So this becomes 2 plus cosine squared t sine t. And now the tricky part. We need to multiply that times the square root of the derivative of x with respect to t, which is negative sine t, squared, plus the derivative of y with respect to t, which is cosine t, squared dt. And that is nice, right? This just becomes sine squared t plus cosine squared t, which is 1. Square root of 1 is 1. So luckily for us, that whole thing just kind of goes away. And now we can integrate this with respect to t. And I can do these separately because I have addition. So the antiderivative of 2 with respect to t is 2t. And then this right here, when we take the antiderivative of this is a basic u substitution. You can let u be equal to cosine t. Derivative of that is negative sine t dt. So negative du is equal to sine t dt. So this should become negative 1/3 cosine cube t. Do I need to show that, or is that okay with everyone? Think you could get that on your own? This just becomes u squared times the sine t dt becomes negative du. So you're trying to take the antiderivative of negative u squared, which is negative 1/3 u cubed. And u is cosine. We're good? I can keep going? I'm going to need you all to tell me to just slow down or go back on something because I'm going to be trying to move fast here today. All right, we want to evaluate that from 0 to pi. Okay, let's plug in pi first. We get 2 pi minus 1/3. What is cosine of pi?
-1.
-1, and then we're going to cube it. So it'll stay -1, but I'll just leave it like that. Minus, now we plug in 0, and be careful here. 0 there gives you 0. Then minus 1/3, what is cosine of 0?
+1.
1, right? So 1 cubed there. So we'll get here 2 pi. This will be a minus 1, and then minus again, so plus 1/3. And then here we'll have minus, and then minus again, so plus 1/3 again. So we get 2 pi plus 2/3. And of course, we could get that as a decimal, but that's the exact answer. So the area underneath that, the area of that curtain drop down would be 2 pi plus 2/3. Questions? You happy? All right, moving on. Okay, so now, what if your curve on the ground, C, is the union of a finite number of smooth curves, C1, C2, C3? So in other words, like in the past example, the curve on the ground was just a semicircle. But what if the curve on the ground is just a bunch of other curves put together? How can we find the area underneath that entire curtain? This tells us that the area of that curtain over C would just be the sum of each of the areas of each of the curtains if we break up the curve. So I'm going to show you a picture of this so you can kind of see what's happening here. So here is a function. We'll work through the example. I'm going to show you the picture first. So what we have is on top, we have the surface is a plane. Okay, everyone see that plane? And on the ground, the curve on the ground, C is this curve, the entire thing, all right? But we can see that, well, hopefully you can see that that curve on the ground is actually like this curve. And if we stop here and continue on, there's another curve there. So we could call this C1 and call this C2. So the area of the curtain will be the area along both of those added up together. So they're two different curtains, and we'll just add the two areas. So we have to break this single line integral into two smaller ones. And that's what the previous property said, is that if C can be looked at as the union of multiple paths, then you're just going to get the line integral for each path and just add the answers up. So let's do that for this one. So find the line integral over the path C of 2x with respect to arc length, where C1 is this parabola. So C1 is y equals x squared, and it's going from the point 0, 0 to the point 1, 1. Let's draw that first. Okay, let's draw that one. So it's this parabola, and it's going from 0, 0 up to 1, 1. And then C2 is the line segment. So it's the line segment that goes from 1, 1 to 1, 2. So if I draw that, it actually picks up at 1, 1. And it goes to 1, 2, which is straight up like this. That's C2. So we have we basically have to do two different problems, okay? We have to say that this line integral we're looking for should be the line integral over C1 of 2x ds plus the line integral over C2 of 2x ds. See, I've just broken it up. C has now broken up into two pieces, C1 and C2. Let's start with the first integral. We'll call this integral A, okay? So for integral A, we need the line integral over C1 of 2x ds, which for us should turn into, all right, we need the parametric representation of that parabola. So I think this is where Daniel, what Daniel was saying on the previous example, this would work out nice for us. Because to draw a parabola, we could just let x be t, and then we could let y be t squared. So if x is t and y is t squared, we should get this function, right? And what should my restrictions on t be? Well, t is really x, right? So x goes from 0 to 1, so t should go from 0 to 1. I also need, within this formula I'm going to use, I also need the derivatives of those. So dx dt should be 1. And dy dt should be 2t. And now I'm going to just rewrite this integral. So integral should go from 0 to 1. And then 2 times what?
T.
Yeah, x, but x is t, right? So this is just going to be t. And then times ds, but ds is the square root of the derivative of x with respect to t, that's 1 squared, 1 squared is 1, plus the derivative of y with respect to t, but squared, so that should give me 4t squared dt. Any questions here? I'm going to pull the 2 out. How can we do this integration? Anyone see what we're going to use?
Is it also u sub?
Just a basic u sub. Yeah. If I let u be equal to everything underneath the square root, the derivative of that would be 8t dt. We don't have an 8. We actually just have a t. So I'm going to just scale everything by 1/8. Which means that integral turns into 2. There's a square root of u, and then there's a 1/8 du. So all I'm doing here is I'm rewriting this integral in terms of u. Replace the 1 plus 4t squared with u. T dt turns into 1/8 du, and I still have the 2 on the outside. It becomes 1/4 integral of u to the half du. And then I use the power rule, which gives me 1/4 times 2/3 u to the 3/2 plus a constant. And then I replace u with the original substitution. All right, so this is going to become, let's see, 1/6, because I put the, I reduced this, this is 2/12, so that's 1/6. U, which is 1 plus 4t squared to the 3/2, evaluated from 0 to 1. Questions? Equals. All right, so if we plug in 1, get 1 squared is 1 times 4. That's 4 plus 1 is 5. So we have 5, well, 1/6 here, and then we have 5 to the 3/2, right? That's what that is. And then minus, if we plug in 0, we don't get 0. Be careful here. We get, this is 0, but then we have a 1 there. So 1 to any power is still 1. So we just get a minus 1/6 here. I mean, that's it. I mean, I'm not going to go any further with that. We could get a decimal, but I'm just going to leave it like this. That's some number, right? We could get, we could pull the 1/6 out. We could get, there's a lot of different ways we could write that, but I'm happy with that. That's the exact answer. So up to this point, here's what we have. We have found the area of this part of the curtain from here to here, because that's over C1. We now need the area of this one. So now I need the second integral, which I'll call B. And
I have
for
a
B-
question.
Yes, go ahead.
So if we go back to that picture, to me, it looks extremely uniform. So if we say, since it's, we're looking at it from a plane and we can like realize it's uniform, we could kind of do some like math magic and kind
Oh
of
yeah,
just,
just like the
get
area
the-
of a rectangle.
exactly.
Yeah, you could do that. Yeah.
Okay.
For this one, I mean, that would be just a shortcut for this particular problem because it's a plane and it looks perfect. But if that plane had just a slightly different pitch to it, you wouldn't be able to do it. Not easily. This one, because it's a rectangle, it would work. But look, the line integral is not going to be that bad either. Okay. The hardest part of the line integral is getting the parametric representation of this, which you may be sitting here going like, how do we do the parametric equations of a line segment? But we actually have done this. I'll remind you that when we have a line segment like this, we can look at it as a vector function that draws a line where we have R0 plus TV. Now just follow me through this. We have our first point, which is the point 1, 1. Our second point is the point 1, 2. And so when we're putting the vector equation for a line segment, what we do is we start at our starting point. It's very important that we're starting at the correct point, which is 1, 1. So we write that as a vector. Plus t times, now the v is the direction vector. And Fabiola would tell you that to get the direction vector given 2 points, that you have to take this and subtract that. So take this and subtract that. So our vector should be the vector 0, 1. And then that should be, if we put these together, this should be just 1, 1 plus t. So I distributed the t through here. And then I put these two vectors together and I get this. Now, if you do this correctly, like the way I have presented it to you in this class, if you restrict it between 0 and 1, then I can guarantee you that it'll draw you just that line segment starting here and ending here. Are you all with me? All right, what about the parametric equations then? What would x be and what would y be?
X equals 1,
X is just 1 and y is
1 plus t.
1 plus t. So this goes back to when we talked about lines, vector equations of lines. We said that when you have a vector equation of a line, you have a vector equation, you have the parametric equations, and then you have what we're called the symmetric equations. So the parametrics are just grab the x here, grab the y, and there they are, boom, right there. Now what's nice is that I need to take the derivative of these with respect to t, which gives me 0, and then this one is just 1. And I think I'm ready. This should be the integral from 0 to 1, because that's my restriction on t. And don't forget, we're doing 2x, right? 2x. So 2 times that x for us would be 2 times 1. 1 because we're using this x this time, right? Not the x we used for the other one. where is it, up here? The x for the other curve was t, here the x is 1. And then we have the square root of dx dt squared plus dy dt squared. And so this should just give me the integral from 0 to 1 of 2 dt. And that's just going to be 2t evaluated at 0 and 1. And that's just going to give me 2. So final answer. Line integral over c, the whole thing of 2x ds should be 1/6 times 5 to the 3/2 minus 1/6. And then add to that the other area, which was 2. And then whatever that is, that's your answer. See how critical it is, though, to get the right parametric equations? Like if you can't get the parametric equations of the curve, then everything else can be off, right? All right, moving on. Now, there are 2 other line integrals that actually come up later on. And they're a little different than the one we just did. Okay, so what we just did right now is the line integral with respect to arc length looks like this. Pardon? I didn't hear that. Not hearing you, Adam, sorry. Am I the only one not hearing him?
No, he's popping.
Okay. Sorry, Adam.
Just try typing it out.
Yeah, you might chat it to me, even though I never look at the chat. I'll look at it this time if you're. Okay, so this is the integral, this is the line integral with respect to arc length, right? We have a little ds here. There's 2 others that we could have. One of them is called the line integral along C with respect to x. And the other one is the line integral along C with respect to y. And the only difference between these and the original is that we're no longer doing ds. Here we put dx. And notice that it's just, this is the only difference right here, okay? So I want you to see what it is. Remember, ds means the square root of, I'll call it x prime of t squared plus y prime of t squared. That's what ds is, right? I'm just writing, instead of writing dx dt and dy dt, I just wrote it as x prime and y prime. Yeah. If we make this be 0, right? If this is 0, then this becomes the square root of the derivative squared, which just gives you the derivative, and that's this piece right here. So the line integral along C with respect to x means you're letting the y prime be 0, and then the other one, you're letting the x prime be 0. So what is that visually? Okay, so let's go back to this. Let's go back to a problem like this. We would like to, this right here, that curtain right there, is the area of that is the line integral along C with respect to arc length, right? ds, that's what that is. dx, if we do it with respect to x, here's what it is. It's like the projection of that curtain onto the xz plane. So it's the area of that, looking at it from this perspective. Do you all kind of see that? It's like if I turn this and just project that onto the xz plane, we're trying to find that area. That's what the line integral with respect to x is. With respect to y, the shadow is cast to the other plane, the yz plane. And so this area and this area are not necessarily the same, and they're not necessarily the same as the green area. All 3 of these give you different answers. But do you understand, like, visually what they are? Okay, now they do appear later. That's why we need to discuss them. All right, so this is just notation. This is just notation, and I actually wrote this backwards. I should start with this on the left and then have the other one on the right. But this is saying that whenever you see a line integral over C, now they're using P of xy instead of f of xy. They're using P, capital P is the name of the function. So that's some surface. If you do the line integral and then put dx next to it and then put plus another surface, a different surface, and then put dy next to it, all that means is you split it up into two integrals and you do the first one with respect to x and the second one with respect to y. So this is just notation, that's all it is. So we're going to do this example. So find the line integral along C of sine x. Okay, so let me rewrite what this is using the property I just gave you right here. This means the line integral along C of sine x dx plus the line integral along C of cosine y dy. That's what we need to do. Now, C is the top half of the circle, x squared plus y squared equals 1, from the point 1, 0 to the point -1, 0, and the line segment from -1, 0 to -2, 3. So let me try and draw C now. So C is the unit circle top half. Starts here at 1, 0, ends here at -1, 0. So we're going to move along this path like this. And then once we get there, we need to go from -1, 0 to -2, +3. 1, 2, 3, way up here. 2, 3. Oh, shit, I missed. Okay. There we go. So that's the whole thing together is C. But obviously, since these are different curves, we're going to have to break it up into two pieces. So we're going to call this C1 and we'll call this other one C2. Any questions on that? That means that this integral has to split into two integrals. Line integral over C1 of sine of x dx plus the line integral over C2 of sine x dx. And then we have plus, and now this splits into, this one will split into two. Line integral over C1 of cosine of y dy plus the line integral over C2 of cosine y dy. We good? Now let's go look at C1 and C2. Let's find their parametric representations. Let's find the restrictions on T. Let's find their derivatives. So C1, we already did this. C1, the parametric is cosine T sine T. The derivatives of those, I'll go ahead and get them now. Again, because we've done these. And I know my restriction on T goes from 0 to pi. All right, for C2, it's a line segment that goes from -1, 0 to the point 2, 3. That's a line segment. So I'm going to do a vector equation. I'm going to start at -1, 0. What's my direction vector? What's my direction vector?
3, 3.
3, 3. Okay, and so now let me see if well, I'll put them together first. R of T equals -1 plus 3T and then comma 3T. And of course, my restriction will be between 0 and 1. And that should draw it for me. From here, I can write the parametrics. And then I'll take their derivatives. Whew, okay. Any questions up to that point?
Sorry, so
All right.
my question here is that what exactly are we trying to find right now? Is it those both of the projected areas
Yes.
simultaneously?
Yeah, so we're trying to find, like, if you were to take this curve, well, we can't see the surface above this,
Mhm.
but if we could see the surface above this, that curtain, we're trying to project it onto the XZ plane, find that area, and then we're projecting along the YZ plane and finding that area
Okay, so,
and adding them up.
okay, so, yeah, all right, awesome.
Okay, so I'm not going to work all these out. I'm just going to set up all the integrals. So let's do the first one. So the first integral will be the integral from, let's see, we're going along C1, right? So it's going to go from 0 to pi. I'll make this a little bigger. 0 to pi. Sine of x. So sine of what's x?
Cosine of t.
It's cosine of t. Times now dx. Now come up here, remember the formula here. The line integral along C with respect to x is this. This dx really is just the derivative of the x function with respect to t. So I'm just going to put here for the dx, I'm going to put the derivative of just this one with respect to t, which is negative sine t dt. You think you could do that integral? Basic u sub, u is cosine t, the derivative of that is this. So you'll have like sine u, I'll let you do that. Okay, plus now this one. Okay, integral, now we're still doing the same integrand, right? It's with respect to x, we're going along C2 now, here's C2 right here. So I'm gonna go sine of x, but this time x is -1 plus 3t. And then what is my dx replaced with? What's that?
3.
It's just this 3 right here. Yeah, it's just 3 and then dt. Okay, 2 down, 2 to go. I'm gonna run out of room, so I'm gonna say plus, and now the next one would be, I'm gonna put it right here. Integral, now we're going along C1 again, right? So along C1 is from 0 to pi. This time it's cosine of y. But if we're on C1, y is sine of t. And then times dy, which is derivative of sine t, which is cosine t, dt. And now finally the last integral. So plus integral, now I'm on C2, so I'm going to go from 0 to 1 again. And I'm doing cosine and cosine of y this time is 3t. And then the derivative of that is dy is 3 and then dt. There you go. Oh, I forgot, sorry, I forgot my limits of integration on this integral. It's on C2, so it should have been from 0 to 1. So each of these integrals would give you a numerical answer, add them all up, and that would be equal to the line integral over C, the whole curve, of sine x dx plus cosine y dy. Questions there? Okay.
I
Now-
have a question.
Yes, go ahead.
The way that you split up C1 and C2 by like using sine and cosine, would we be able to just find the integral of just C1 and then add that plus C2, or do we always have to split them up the way you did, right? Do you know what I mean?
Could you do the integral of C1?
Because you did sine x dx plus cosine or cosine y dy, but you split them up by C1, C2, and I guess I was just wondering if you could find the integral of just C1 using sine and cosine, and then add that.
Here's what you could do. You could write both of these together, but it would be the integral over C1 of sine x dx plus cosine y dy, like that. Is that what you mean?
Yeah, I did. Yeah, I was just wondering if I ever took that path, would it ever lead to the wrong?
No, you just have to be careful with something here because it's all about notation. This really does mean just two integrals, right? So if you do this right here, that's this first one right here, this becomes sine of cosine t negative sine t dt. That's what that is. And then you have plus
Okay, yeah, I
another
see.
one. So you see you have like dt twice in here. It's just
Yeah,
weird notation. So it's just,
messy.
yeah, just put two integrals and do them separately is probably
Okay.
going to keep you out of trouble though. Okay, now this is now, we finally have got to a question here. Like a kind of an interesting question. What happens if we change, that should say what happens if we change the orientation of the path? In other words, what if we traverse the path backwards? So look, do y'all agree that we have this curve here, C, right? This curve and this curve over here are the same curve, right? But when we create a parametric equation, we're going to start at one point and end at the other, and we're going to move in like a direction. So one way we could do it is to go from A to B, right? Or we could go from B to A, right? Those are both the same curve, but we're traversing them in opposite directions. So if we call this from A to B, if we call that path C, then going the opposite direction we call negative C. Right, so the negative in front of the C just means the reverse direction of the path. Do you think that gives you a different answer?
I think it should.
You think so?
We
you
wouldn't be
don't.
talking about it if it
No.
didn't.
There
Yeah.
could be a rule that says that the backwards, that there's like just a rule of like the forward is equal to the negative of the backward.
Yeah, okay, so that's the part. Remember what the line integrals represent, right? The line integral represents the area underneath the curtain, right? With respect to arc length. With respect to X and Y are just the shadows cast upon the planes. You would think that you should always get positive answers. But if you think back to the rectangle on the ground, let's go back to the very first example we had, where we had this semicircle on the ground, and then above it, we had the path of that up there, whatever it was, and then we were dropping the curtain down. And I said, we're going to take this rectangle. And we said that little piece on the ground there, we said is the square root of something, blah, blah, blah. This should always be a positive number, shouldn't it? The square root of something should always be positive. And so this is always going to give you a positive width, and then you do the function's height, multiply them together, you get the area. So since this will always be positive, changing the direction of the path should not matter. It should be the same both ways, because that's a hypotenuse of a triangle. However, if you take this would be really hard to do, but if you imagine that black piece projected over onto this plane here, and think about that rectangle up here, then it does matter if we're moving this direction versus this direction. This change in X is either going to be positive or negative, depending on which way we go, right? So the conclusion of this is this. Here's the connection between integrating over C versus negative C, which is the reverse path. If you're talking about with respect to X, then what happens is you have a sign change. Whatever your answer is, you just change the sign if you go backwards. So let's say this line integral gave you the answer of 4. Then if you go backwards along the path, you'll get -4. Same thing happens when you have it with respect to Y. If you get an answer here like 10, then the answer traversing backwards will be -10. If it's with respect to arc length, it does not matter which way you traverse. You'll get the same answer. If this is 4, that's 4. Okay, this is just kind of an FYI thing as we move ahead.
So in like the depiction of it, would it be that instead of projecting it onto the plane above the XY plane, it would be below? So it'd be like a negative area, I guess? Just like how we had the negative volume?
No, it has to do with this. It actually has to do with this. Back in Cal 2, when you're integrating a function from A to B, when you're doing that, the width of your rectangle right here, this is your change in X. And your change in X is going to be this point, whatever that number is, minus this point right here, whatever that number is. And then, oh, sorry, I don't want a fraction, just that number minus another number. And do you agree that that would be positive number? Like, take a number to the right and subtract the one on the left, and then you're going to get a positive number here, right? And so that the integral from A to B of f of x dx, that area will give you some answer. But if you reverse it and you go from B to A, then what you're doing is you're taking this number and subtracting that number. And that will always be a negative number. And so by reversing the limits of integration, this becomes negative of that answer. So this is a property from Cal 2 you may not remember. If you want to take the integral from A to B of some function, then switching and going from B to A, all it does is gives you the opposite answer. That's all. So that's really what's happening here. It's not that the area is above or below. It's that the little dx on the ground is now negative instead of positive. Does that make sense, Adam? I think Adam.
Yes, yes.
Okay. Okay. I'm continuing. Okay, so we already know that if you traverse the path in opposite direction, it may or may not have an impact, but it's only going to change the sign at the most, right? But what if it's a different path, but connecting the same two endpoints? So what if you have a path here from A to B that, let's say the path C that goes along this and then gets here and ends at B. If we do a line integral along that path, how do you think it's related to the line integral along the straight line path connecting A and B called C tilde? Do you think we should get the same answer?
Completely different answer.
Generally, we should get a different answer, right? Because this is the area underneath, right? This curtain, those would be two different curtains, right? That'd be two different curtains. So in this next problem, we're asked to try and determine that on our own. It says, do this line integral over C where along these two different C's. Okay, so this C is one of them, and then it's a different problem with a different C. They both start at the same endpoint, or start at the same point, end at the same point. And so it's just to compare, do we get the same answer? So I think what I'm going to do on this is set them up, but I won't compute them. All right, maybe we'll have the computer compute them. All right, so let's talk about this. Let's call this second one C tilde, so we don't confuse them. Let's talk about C. C is the parabola x equals 4 minus y squared from -5, -3 to 0, 2. All right, so for this parabola, we draw this. It's a parabola that opens sideways to something like that. This should be here at 4. So let's start with the parametric. This will be interesting to see if you can come up with the parametrics. Who can give me the parametric equations for that parabola? It's solve for x, not y, right?
So then it's 4 minus y squared.
X will be 4 minus, not y squared. You're on the right track.
T squared.
T squared, and y is t, right? So this is just like when we had, if you have a function where y is y is a function of x, we replace x with t and just write down the y in terms of t. Here, if it's solved for x, we replace the y with t and write down the x as a function of t. Now, you have to figure out what the restrictions are, though. What are your restrictions on t? You want to start out at -5, -3.
Would it just be the y value of the endpoint?
Well, what t value would start you here? Like, what t do I plug in here and here to give me? Oh, you mean, is it just this y value right here? Is that what you mean?
Yes, yes.
Oh, okay, yes. Because the y is t, you can just look at the y value. Yes, for this particular problem. I thought you were asking me more like in general. I'm sorry. That is correct. If t is -3, you plug -3 in here, you get 9. 4 minus 9 gives you -5. That's this. And then, of course, y is -3. Okay, I'm going to need derivatives. dx dt, -2t, dy dt. Just going to get these just to have them. Okay, you ready for this integral? Line integral over c of y squared dx plus x dy. By definition means line integral over c of y squared dx plus the line integral over c of x dy. That's just the property that I split these two up. Now this equals the line, the integral from -3 to 2 of y squared. What's y squared for us?
T squared.
D squared times what's dx?
1.
Oh, careful, that's
negative
dy.
2t.
-2t, right? -2t dt plus integral from -3 to 2. And now x is this. And then dy, but dy is 1. So at the end of the day, this is really just -3 to 2 of -2t cubed plus 4 minus t squared dt. So all I did here is I put these two integrals back together since they're both with respect to t. I put them together, I put that, I got -2t cubed. Then I did plus the 4 and minus the t squared. I still need to integrate that, right? So I'm going to stop there. Are there any questions on that? Okay, that was all over C. Let's do C tilde now. C tilde goes from -5,3 to 0,2. Straight line, right? 0,2, yeah. Straight line for this. So I'll just do a vector equation of a line. I'm starting out at -5, -3. And I'm ending at the other point. So my direction vector, remember, I'm going from here to there. So I subtract 5, 5. Is that what you get? 5, 5 is a direction vector. Putting those together, I'm going to save us some time. This should be -5 plus 5t. And then the y should be -3 plus 5t. I realize I'm moving fast. Getting derivatives because I'm going to need them.
Real quick. So I can see here that we're gonna apply the direction, because if you would go from the one point to the other, so the opposite direction, then it would be traversing it in the negative direction, right? Negative C.
Mhm.
So would that make a difference?
Wait a
We would
minute,
just have
say
to
that
do the
again?
sign change.
Say that again?
Because if we would go from 0 to 2 to -5, -3,
Yeah.
the other way, then we would be going backwards on the curve,
Yes,
right?
which means our answer would differ from going this direction by just a sign.
Yeah.
But that's only
So-
because these are with respect to X and Y.
Mhm.
If this would have been with respect to arc length, there would be no change in the sign.
Okay.
Okay, I think I'm gonna set this integral up. Here it is again, right? This is it. This is what we're gonna do. But it's over C tilde. I'm gonna change that to C tilde, C tilde, C tilde. And so now this will be equal to, oh, I forgot to put 0 to 1 here. Sorry, everyone. T goes from 0 to 1. All line segments will go from 0 to 1, so long as you set them up properly the way I've shown you. So 0 to 1, okay, y squared, which will be all of that squared. And then dx, but dx is 5. Plus integral from 0 to 1. And then x, but x for us is this, -5 plus 5t. But then times dy, but dy is 5, and then dt. And then you could put both of those together. Let me try and put those together into one final answer. Integral 0 to 1. Oh shit, I don't feel like squaring that. -5 plus 5t squared plus, oh, times 5 again. I'll put the 5 out front. Plus 5, and then -5 plus 5t, all of that dt. So I'm not going to go this. I'm not even going to check it on a computer. You'll just have to, you know, trust that if you did these two, you get two different answers. Questions? So given 2 points A and B, what happens if we choose two different paths connecting them? Does it change the value of the path integral? Answer: in general, the line integral depends on the path. If we change the path, it is likely to change the line integral will change. There are some conditions which make the value of the line integral independent from the path we choose, and we'll address that later. Sometimes the path doesn't matter. Okay, everything we've been doing up to this point, the C that we've been looking at, the curve C, has been on the ground, then there's been a surface, and we've been dropping a curtain down, right? Now, let's let the C be in three-dimensional space. The function is in four-dimensional space, and we're trying to find an area that you can't even visualize anymore. So I can't show you a picture that goes with this. Does that make sense? That I can't. But one way to think about how you could like see the use of something like this is to think about an object traveling through three-dimensional space, okay? And maybe at each point in time, okay, as you move along this path, at each point in time, you're measuring the, I don't know, what could we be measuring? Temperature doesn't make a lot of sense here, but we could just use it as an idea, because if you're moving through space, at each point in time, there should be some temperature corresponding to where you are, right? So your function of X, Y, and Z is somehow giving you your temperature at each point at X, Y, Z, right? then the line integral along C of this with respect to arc length should give you like the total of all the temperatures added up together. Although that doesn't have a lot of meaning, okay? Like what's the sum of the temperatures along your path? You could think about it maybe as like your, how about your mass? I'm sorry, your, yeah, how about, what if it was, if this was a wire, a three-dimensional wire, and that we were able to compute the mass at each point, right? The mass at each point, then this line integral over C with respect to arc length would give us the total mass of the entire wire. And then, believe it or not, you could actually find the center of mass, which may not even be on the object itself. It may just be some point in space that the wire is not even part of. All right, so I'm just trying to show you these do have some value to them, right? Is everyone clear that the center of mass of an object does not have to be on the object? Right, like if you just take a ball, right? Just take a sphere, right? A basketball, the center of mass is in the middle and that's not on the sphere. So, okay, so what changes? Everything is exactly the same. It's now we have this three-dimensional idea. So this is the notation for the line integral. It's the same thing, single integral over C, but now we have f of x, y, z because we have three pieces now to the function. And then ds is still the same, but the ds is now the square root of the sum of all three of the derivatives squared and added together. That still does represent a hypotenuse of something, but it's in three-dimensional space instead of two-dimensional space. That okay? But something really good is about to happen, all right, with our notation. I want everyone to try and understand that this line integral can now be written this way. Okay, whoa, what is that? Well, what we're saying is if the curve C is this curve that lives in three-dimensional space, right? Curves in three-dimensional space, we learned back in chapter 10 that all curves in three-dimensional space can be drawn with vector functions. So this represents that curve. If this represents that curve, then evaluating the function at each point x, y, and z really means evaluating the function along the vector function. So this is a weird notation. This is the first time we've ever seen this notation, which is why I say, please make note that f of r of t, the vector function r of t, means we plug the component functions of r into the scalar function f. I will show you this in an example. But the cool thing is, well, let me do it this way. Remember, this vector function should be some function of t, some other function of t, and some other function of t. It should have three components. Each one is a component function. So if I were to ask you for the magnitude of this vector, right? It just so happens that if I ask you for the magnitude of that, what you're going to do is the square root of the derivative of the vector function, right? Let me do it this way. You're going to try and find the magnitude of the derivative, right? What's the derivative of that? Well, you just take derivative of each one, right? And then to find the magnitude of a vector, you take the square root of the sum of all three of these squared, which is exactly what this is, or without the dt. This happens to be this. Do you all see that? It's the derivative of the x function, this one, squared, plus derivative of the y function squared, derivative of the z function squared. And so what we have is just a new way of writing this, and it involves vectors. That's a first for us. So I'm going to go to an example. Oh, wait, hold on. I'm not going to go to an example. So this is new notation. This is the line integral along C with respect to arc length. But just like before, we have different versions of this where we can go with respect to X, with respect to Y, or now with respect to Z. And the only thing that changes is dx here, dy here, and dz here instead of ds. Some additional notation. If you see all three of these written together, this is real important as far as notation. If we have a line integral over C of some P function with respect to X, Q with respect to Y, R with respect to Z, it really means just do all three separately. And there you go. I'm going to let you see if you can, let's see if you can at least get this started. Okay. And I'm going to bring it up on a different page so it has the formulas that you need. Here we go. So here's the example I want you to try and set up. And I don't want you to evaluate the integrals. I just want to see if you can set them up. And these are the formulas you should need for that. Okay, and I'll give you about 10 minutes, see how far you can get, and then I will come back and we'll just look at what the answer should be. I'm going to start working it out, and then you can kind of look up and see if we're doing the same thing. Okay, I moved very quickly through that, but I believe that's it. I'll briefly discuss this. We have a line integral over C, and then we've got these with respect to X, Y, and Z respectively. And we're going over C, which consists of two line segments. So I'm going to do these in two different curves, C1 and C2. So I first find the parametric representation of this line segment. I'm in three-dimensional space. So I start with the vector 0, 0, 0, plus t times the direction vector from here to here is going to be that. T goes between 0 and 1. Distribute the t through. Here's my vector function. X component, Y component, Z component, derivatives of each one. Then I do the same thing for C2, which would go from here to here. Vector function, distribute t. Here's my X, Y, and Z components and their derivatives. Questions on that? Then this integral really needs to be this integral over C1 plus this integral over C2. So here it is over C1. Here it is over C2. And since they were added together, I just do three separate integrals for each one. So x squared, y squared, z squared, x squared, y squared, z squared. And then I just go and start replacing. I'm on C1, so I'm looking at this one. And I just replace x with t, and I replace dx with 1. I just do that for each one of these. And now I've got to figure out what all those are, except for that one. That one's 0.
You said the interval will always be 0 to 1.
For a line segment, yes. If you do it the way that I've shown you, which is to always put your R naught, this right here always has to be where you're starting, right here, where you're starting. And then your direction vector must be created by going from your starting point to your ending point. If your direction vector is created that way, then I always go from 0 to 1. Okay, we're going to move on. Okay. All right, now we need to kind of clear our minds a little bit now, right? Everything we've been doing, the integrand, this here has been a scalar function, meaning, and this is pretty much everything we've done in this class and Cal 2 up to this point. In Cal 2, when we were doing f of x dx, that was a scalar function. When we were doing double integrals over x, f of x, y with respect to area, this was scalar. The f of x, y, we were doing triple integrals, f of x, y, z, dv, these were all scalar functions. Today, we're doing line integrals over C of f of x, y, ds, or we could do line integral over C of f of x, y, z, ds. These could also be dx or dy here, or this could be dx, dy, or dz. All of these are integrals where the integrand is a scalar function. When I say scalar function, I do not mean that it's just a number. Like normally when we think scalar, we think like a number. Scalar function means that it is just a function of x and y. There are no vectors involved, okay? It's just like x squared y or sine of x plus y or something like that. Everything is nice. Now what we're going to do is line integrals over vector fields. So this is a completely different sort of idea in terms of what we're trying to accomplish. And the main idea, I guess, is that what we're going to be integrating now, the integrand, is now going to be a vector function instead of a scalar function. But let's just see what would motivate this. Like, where would it come from? Why would we even be thinking this way? Okay, so remember, back in chapter 10, section 3, work is defined as follows. Work is always equal to some force vector dotted with, not multiplied, dotted with the displacement vector. And you probably know this if you've taken any physics classes. Work is always force vector dotted with displacement vector. That gives you the work. So if we have a point, or let's say we're looking at some point here. Let's say I apply a force, and I can change this force. The force is a vector because if I change the length, that means there's more force. And then I can change the direction also, right? So I apply some force, and then I have a displacement vector, which is a direction of displacement. And then if I dot those two, that's this number. If I dot the two, get a dot product, right? And that number represents the work done. If I change my force vector to go past perpendicular, I get a negative dot product, which means negative work. All right, so that's the general idea. If you're at a point and you have force and a displacement vector, then you have work. Now what we're going to do is imagine a point moving along a curve in space. Okay, a point that's going to move along some curve. And throughout that space, there's a vector field. So that field, that force field, could be a vector field, or it could be, it could be a gravitational field, electromagnetic field, whatever it is. There's some vector field that your point is moving on a curve through that space. Then the total work done by the field is the sum of all the work done at each point. So here's a picture. So we have a curve. See the blue curve here? And we're going to be moving a point along this curve, and there's a vector field in place. Okay, remember the vector field, there's vectors everywhere. We just can't show them all because then it'll just cover the whole screen. But at every point there is some vector. Now that vector, we're going to say if this is like gravitation or electromagnetic field, then that point is, there's a force being applied to that point, right? And that red vector represents that force. Now, this is not drawn to scale. If I move to different points on the curve, you can see that the force vector changes, and it's following this general curvature of the field. So if I move it, it's going to start to pitch downward, the red vector. You'll see how it kind of follows this circular pattern. Let me get some more vectors in there. Yeah, maybe that'll help. So also notice the length of the vector is changing, right? It's bigger, big, long vector, but as I get closer to the x-axis, it got shorter. So I need to back up. Let me start somewhere. Okay, so let's say we start at this point right here. Okay, so I'm going to say, let's start at that point. I want to move along this curve, and I want to end, let's say, here. As I move through here, at each point as I move, I have a force vector. Oops. At each point as I move, I have a force vector, which is, what the hell?
So wait, I just want to make sure I have the right idea. Every vector is a force, and that path is our direction, where we are going.
The path gives us the direction because we have the force vector. The displacement vector is actually parallel to the tangent vector, right? And we know if we're given a curve, we can find the tangent vector, can't we?
Yes.
And capital T, it's hard to see that says capital T. Capital T is the unit tangent vector. So it's a vector that's tangent, but it also has a length of 1. Yes?
Yes.
So if I'm moving from point to point along this curve, I want to imagine taking an infinitesimally small displacement. Okay, so this really small, I'm going to have to, there's no way I can zoom in. Here's that black point. Then I've got this like tangent vector that's running this way. Maybe I'll do a different color. Let's make the tangent vector blue. Okay, that's my tangent vector and unit tangent vector. And then I have the force vector, which is pointed down. This force vector is the force vector. This unit tangent vector is not the displacement vector. It's not, because I'm not going to move that far. I want to imagine moving an infinitesimal amount, just a tiny little infinitesimal amount. The unit tangent vector will give me the direction of that, okay? What I'd like to do is scale it back to make it infinitesimally small. How small? Well, how about as small as the little curvature of that path, the little arc length of that path, right? Because as I move through this path, if I exaggerate the curve, shit, that's terrible. If I exaggerate the curve, here's the curve, right? I'm moving along that curve. I'm trying to figure out how far am I moving in that direction? Well, I take the unit tangent vector and I scale it by how big that little patch is right there, that little curve of the arc, which is the arc length. So if I take that force vector, I dot it with a scalar multiple of the tangent vector. Now, what am I scaling it by? How about let's scale it by the arc length. You see, this is a number, right? That little arc length is a number. This right here will give me the D. That'll give me my little infinitesimal displacement vector. And I do that along the entire curve. And if I add them all up, I get the work done moving through that field from one point to the other. Does that kind of make sense?
Yeah, there's a lot going on, but I think I got it.
Yeah, it's a lot to kind of comprehend because we haven't really talked about this. I mean, we've talked about vector fields. We've talked a little bit about work, but we're putting it all together now. And so as you move across this curve, at every single point, there's a different F, right? At every point, there's a different F. At every point, there's a different tangent vector. And at every point, there's a different little ds. And then you just sum them all up. So you bring in the integral.
But now we need to know how to integrate a dot product, right?
That's right. That's right. But that's okay because dot products give us nice answers, don't they?
They give us numbers.
They give us numbers. Well, in the case of if we had functions, two vectors that had functions in them, we dotted them, we would then get a scalar function, wouldn't we?
Yes.
Okay, so that, and we know how to do scalar functions. So here's the final, not final result, but here's kind of the big picture here. Okay, we can see that the work done at each point is F dotted with ds times the unit tangent vector, some scalar multiple of the tangent vector. And as before, adding these up, if we were to add an infinitely many of these, we would get the total work is the line integral of F dot t. I just switched the order of t and ds here. We can do that because it's a scalar. F dot t ds, where r of t is the vector function which draws c. T is restricted between a and b. Capital T is the unit tangent vector to the curve r of t, and f is a given vector field. Okay, so right now, the way it looks, in order to do this, somebody's going to have to give us the vector field. They're going to have to give us the path, r of t. If we know what r of t is, do y'all remember how to get capital T? What's capital T?
That's our direction vector, correct?
It's the unit tangent vector. How do you if I give you r of t, which is the vector function that draws the curve, how do you calculate capital T? Anyone remember?
I'm gonna go on a
Don't you,
limb.
Divided by its magnitude.
yeah,
Yeah, it's the curve itself, it's the vector function itself divided by its own magnitude. That's what capital T was if you look back in your notes. I'm sorry, it's the derivative, sorry, derivative, I forgot the derivative. It's the derivative of the vector function divided by its own length. Okay? So it looks like, again, to do this, we're going to have to be given a vector field, and we're going to have to be given, so that's given, and someone's going to have to give us that. And then once we have that, we're going to have to calculate that. This looks like it's going to suck, doesn't it? But something really, really nice is about to happen. Watch. But since this is equal to that, right, which is what I just said, and because ds is this, okay, let's go back in the notes. Why is ds that? When I introduced these the line integrals in space, and I said three-dimensional, and I said, oh, remember this square root thing? And I said, hey, this though is really this, right? And I just kind of left it alone. I never mentioned it again. The reason I wanted you to see that this is because that's exactly what ds is. I mean, ds is this thing. So that's what this note is saying here, is that since ds is really that, then when we do this work integral, f dot t ds, the t we replace with that, right? And then ds we replace with this, and these cancel. And what you're left with is this. And that's what we're gonna need, and that's what we're gonna use in order to calculate the work done. So what is it? It's F, the field evaluated along the curve, dotted with the derivative of the curve. That dot product will give you a nice scalar function. We integrate it with respect to t. Let's do an example. I always think this stuff is harder when you're trying to learn what's going on until you do an example. You're like, oh, okay. I'll get back to this. Let's do an example. All right. Shit. I don't know if I want to do this. Is this the one I'm supposed to do right now? Yeah, okay. So you know what? I'm going to change this a little bit. No, we'll do it. You're all Cal 3 students. I think you can handle this. All right. Find the work done by the gradient vector field of the scalar function f of x, y equals x plus y quantity squared on a path traversing the top quarter of the unit circle, in the counterclockwise direction. All right, so let's start with this. We want to find the work, right? Work is equal to the integral over c of f evaluated at on some curve, dotted with the derivative of that curve dt. That's what you have to have burned in now, all right? Not burned in, I mean, you're gonna have formula sheets, but that's like the most important formula for work. Okay, so we need a couple of things here. Let's figure out what R of t is first. All right, so we want to be doing the traversing the top quarter of the unit circle. So that's only this part right here. And we want to go counterclockwise direction. So we want to go this way like this. So how about we use this vector function? Cosine t, sine t. And we'll let t go from 0 to pi over 2. So we're going to be moving a point from here through up to here. And in the background, there's a vector field. And so at each point, I'm calculating the work done to move through that vector field. You all right with that part? Now, what's the vector field? Well, this is why it's a little tricky. It's the gradient vector field of that scalar function. So you have to go back to when we studied gradient vector fields. How do you create the gradient vector field from a scalar function? The gradient of a scalar function is equal to a vector function that is made up of the partial derivatives of that vector function. This is what they're telling us they want our capital F to be. Find the work done by the gradient vector field. What's the gradient vector field? Well, that's going to be this. So what are those partials? So what's partial of this with respect to x? I think it's just 2x plus y. Right? Isn't that a derivative of that with respect to x? Bring the 2 down. This to the first power derivative of the inside with respect to x is 1. What's the partial of f with respect to y?
Same thing.
Same thing. So normally in a, normally in a work problem, the vector field is like just given to you. And this problem is a little tricky because they're saying the vector field is the gradient vector field of this. I could have, for the first example, this is why I was like, I don't know if I should do this one. I could have just like given you the vector field to start. But here we had to work for it a little bit. Okay, so here's what I'm gonna do. We're almost out of time. The work done will be the integral from 0 to pi over 2 of, you know what, on this formula, sorry, here, this formula, change that C to AB, sorry. That's AB, because I've already got it in this form. So everything has parameterization on it. So it has to go from A to B. Okay, so here now the vector field evaluated on the curve. So this you've not seen before. All it means is you take your vector field, which is right here, you replace x and y with the parametric functions for x and y. So it'll be 2 cosine t plus sine t, comma, 2 cosine t plus sine t. Okay, that right there is the field evaluated along the curve. Then we want to dot that with another vector, dt. Now that vector is r prime of t, which is the derivative of this, which we know is negative sine t cosine t. Integral, dot product. So when we do dot product, we just multiply those two together, right? And then we multiply those two together and add them up. So if I multiply, I should get, let's see, I'm going to do this all together. 2 sine t cosine t minus, oh, that would be minus, sorry, minus 2 sine squared t. And then I get plus, let's see, 2 cosine squared t plus 2 sine t cosine t dt. Okay, I'm out of time. So I distributed this to here, which means I get a negative sign on both of those, and then I have a 2, so that's that. And I distributed, or not distributed, I multiplied those two, so I should get a 2 cosine squared t, yeah. That looks right. These two cancel. And now you just have to do this integral. And that would be the work. Okay, we're gonna have to pick up from here, but check this out. Look, I don't know if you can tell, these are the notes for this section. I still have example 7, example 8, example 9. Then we can move to the next section. So we've spent all day on this section. We still have more to do. Okay, that's the way it is. I mean, chapter 13 is just really, it's a lot of work, and it's a lot. So, okay, try and do as much as you can on your homework for this. I would say for, where are we, line integrals? I'll just tell you what you should be able to handle up to this point. $37.39. You should be okay with 1 through 13. 19 through 22 is where what we're doing right now starts. So you might want to hold off on those. Just maybe get the first 13 done. Okay. All right, everyone. Have a good day. Sorry I went over on time.
Thank you.
You're welcome. I'll hang out if you have a question.